All right, we're going to go ahead and get started. So thank you all for joining us today for this webinar on mastering blood pressure variability. You may not be able to achieve complete mastery after this session, but my hope is that I'll at least be able to send you on a path to where you better understand the measure, what the data might look like, and then when the data doesn't look quite as you'd like it to, how to handle that with some data editing. So my name is Eric Morgan. I'm the president and CEO of MindWare Technologies. I've been doing this since 2007, and it's been a little while since I've run a webinar, so I'm excited to get back in the swing of things with this. A couple administrative items before we get started. If you happen to have any audio issues, please refer to the Zoom bar, and you can make sure that you have the correct speakers set up. We do have everyone muted just because it can get a little noisy with many people attending the same meeting trying to ask questions. So certainly we invite you to ask questions, just not via the mic. We'll talk about that in just one second. But if you have any issues with audio, let us know. We can troubleshoot with you on the side. As far as questions go, again, via the Zoom toolbar, you can pop open the Q&A panel where you can ask questions. We would encourage you to do this throughout the presentation. You don't have to wait till the end as talking about something and something comes up. Please feel free to do that. We have a few folks on the line from our team who will be able to answer in the moment. And then at the end of the presentation, I'll be coming back around to all of those questions to bring them up to the group if they're relevant so that we can all learn from the questions that are being asked. And no need to be shy. The panelists are the only ones that will be able to see what you ask. So there is no such thing as a bad question. Please ask anything that needs to be asked. And lastly, before we get into the core of the presentation, talking about blood pressure, a brief word from your sponsors, so your sponsors being us, MindWare. I just wanted to bring awareness. We've been trying to bring awareness to the fact that we don't just measure physiology here at MindWare. We actually specialize in a whole spectrum of research technologies that you might benefit from, depending on the questions that you're asking. So an example might be if you're wanting to collect physiology and eye tracking, and also observe the behavior of your subjects as they go through your protocol. We're able to, through our partnerships with other companies, tie all these data streams together to where they all start with the push of a button. They're all synchronized down to the lowest possible common denominator of sample rate between the devices, and then very easily then merge these separate data streams into a way in which you can analyze all of them considering one another, whether that's leveraging third-party tools like Interact or Tobii ProLab, or just using our analysis applications to do so. So we're able to kind of span that entire continuum and bring in these other data points if they're necessary. In addition to that, we do design entire labs. So you don't just have to buy a mobile or a piece of software. If you have a complex question, you have a new space you're wanting to make use of, we regularly engage with researchers to identify places where cameras should be placed, microphones, networking, other equipment that you might need, come into your lab, install it all, train you on it so that you're set up from day one. It's a huge part of our business, is actually where we started as a company back almost 25 years ago. So something that we still do today, and we're able to offer that as needed. And even though I'm going to be talking a lot about analysis today, many of you probably already have our analysis software and you're wanting to learn a bit more about how to use it. If for some reason you don't have the resources or the time to do this work yourself, we can also do that for you. We have a data analysis service where we'll engage with you about your data set and understand what your needs are, advise on analysis strategies, and then you hand it over to us. We analyze it based on all of the best practices that you're seeing here today, and then we deliver it back to you so that you can focus on designing studies and interpreting those results on the back end and leave the grunt work to us. So with that being said, we can jump into the core of the presentation, which is all about blood pressure. And I wanted to start by talking a bit about how you would measure blood pressure. What are the systems that are typically at play here? How are we getting the data into the MindWare ecosystem, which there are many ways to do so? and what are some options in terms of the type of device that we're using? Are we measuring continuous or momentary blood pressure? So I'm going to start by talking about continuous assessment of blood pressure, because when we talk about analyzing blood pressure, editing blood pressure, we're always doing so on the continuous waveform, not momentary blood pressure assessments like you might have at your local pharmacy or at a device that you place on someone's wrist and it takes a single measure. The problem with those devices, and we'll talk about that a bit more later, is that you don't have this stream of data to refer to. You just have the numbers on the screen that represent the systolic and diastolic blood pressures and typically mean arterial pressure. For us to look at something like blood pressure variability or baroreflex sensitivity, some of these more advanced metrics, we really need this continuous stream. Most commonly, we find people are using one of two devices to do this. There's the CNAP, which is sort of our preferred device for this, and that's by a company called CN Systems. And then there's the Finapress Nova. And both operate using this dual approach where there's a cuff on the arm that is taking baseline measurements over time. And then there are additional cuffs, either on the wrist or the fingers, that are maintaining more constant pressure assessments at those extremities. And that's the way in which we're able to get this continuous representation of blood pressure over time. So you can see cycle by cycle, beat by beat, what the diastolic and systolic blood pressures are for that given beat. These devices are often medical grade because they are often used in medical settings. I'm actually not aware of a research grade continuous blood pressure device. Medical grade typically means expensive, and that's often the case with these devices. These are going to be more expensive, certainly, than the momentary options. In terms of integration, for both of the devices that I'm mentioning here, we can just place a cable between that device and our Bionex or another device that we sell, and we can get the data streamed in that way. And it depends kind of on which monitor you're using. If you had a CNAP, then you might bring the data in. You would bring the data in through a transducer module. And if you had a Finapress Nova, you would bring it in through a high-level pass-through. Generally speaking, the transducer modules and the high-level pass-through modules are our integration modules. That's how we get data from third-party systems in. Of course, there are other systems out there, and if you are using another system and you're interested in merging this data and sampling it simultaneously with the ECG, the cardiac impedance, the other measures that you're collecting with your MindWare system, just talk to us. We can almost always figure out a cable that we can build or design to get that data out of that system and into ours. But again, this is really important for many of the things we're going to talk about today. So most of the data, all the data we're going to look at is going to be continuous in nature. That being said, there are other options, and many people opt for this because it's much more attainable. It's much more affordable. The momentary assessment. Basically, you press a button, the cuff inflates, you get your measurement, and then you move on. Of course, you're not getting beat by beat measurements here. You're getting sort of an average depiction of blood pressure within a given period. But some data is better than none, and in many cases, there are approximation methods where you can use these momentary measures to approximate the same things that you might want to with a continuous signal, like a threat versus challenge assessment, which I'll have a slide about in a little bit. Some common systems that we see people using for momentary blood pressure, although there are hundreds of these, you can go to your local pharmacy and find all kinds of them on the shelf. And then there are some more hospital grade ones like the one I have circled here. The GE CareScape is the one that we see most often. If someone comes to us and asks what they should use for momentary blood pressure, we're almost always providing this device. It's nice because we have an integration with it. So even though it is momentary, you have to press a button to take a measure, we can integrate directly to our acquisition software, Biolab, and from the computer actually start those measurements and then receive back into Biolab the results from those measurements to be stored for later use in data analysis. You can't edit it again because, again, there's no waveform. There's just numbers, but at least you have it all in one place, and you can use some strategies to, take measurements at specific frequencies or intervals and use that as an approximate assessment of blood pressure over a period of time. In general, some of these other ones like the Oscar 2, it's an ambulatory blood pressure monitor, which is kind of nice because it's mobile, but suffers the same kind of challenges because it is momentary. Some of these devices don't offer integration capabilities. Like the Oscar 2, you can't pipe the data out of it into something else. It's simply stored and timestamped on the device. So again, something we can help you with if you have these sort of devices and you want to synchronize them with the other physiological recordings. There are rough ways to do it. It's not our preference, hence the fact that we recommend the CareScape, but there are always ways to do those sort of things. So with that being said, and those being the methods by which we can collect this data, I want to talk a bit about the data itself. It's quite important as researchers when we're collecting this data to understand what the data should look like so that before we actually start our protocol, before we, spend that precious time on a subject or a group that have been brought into the lab for an experiment, we want to know that we're getting good data before we start that because we can't afford to lose it. We have such few samples so often. So this slide indicates some key landmarks on the data that you should be familiar with. Generally speaking, you should just know what a blood pressure signal looks like, but it's helpful to know what these landmarks are as well. And so to start the signal, you'll see the diastolic marker, the diastolic pressure being the green circle on the signal here. It's the low point prior to the acceleration of the blood pressure up to its peak. And it's basically indicating the minimal pressure for that cycle. Now, once blood starts to flow out of the aorta, you're going to see this increase in blood pressure as pressure is applied to the arterial walls. And that's going to culminate in systolic pressure. So that is, of course, the maximal pressure following that contraction. And what you're used to reporting blood pressure levels as is systolic over diastolic blood pressure, 120 over 80, which means that amplitude is also relevant here. We don't just want to look at morphology. Morphology is very important, but we also want to pay attention to the signal level to make sure that we are getting the level that we expect. And of course, you can see here on the left-hand side of this graph, I did include the y-axis, and we can see that we're sitting somewhere between 70 and 110, which is a reasonable blood pressure value to expect to have. So we've got diastolic pressure, we've got systolic pressure, and then we have mean arterial pressure, which is calculated using the formula that I've shared here, DBP standing for diastolic blood pressure, SBP standing for systolic blood pressure. And we're going to calculate this on the fly. It doesn't actually require the identification of any other landmarks on the signal. It is just the mean arterial pressure for that cycle. This comes into play particularly if you want to do something like a threat versus challenge assessment and calculating total peripheral resistance. You want to make sure that you're getting clean mean arterial pressures, which subsequently means you want to make sure you're having a cleanly marked diastolic and systolic points on your waveform. The last landmark that I'll mention here, which isn't actually necessarily relevant in terms of psychophysiology, we're not using it for anything. It's certainly used clinically in many ways, is the dichotic notch. And this roughly is associated with the closing of the aortic valve. You get this kind of rebounding pressure that occurs when that valve closes. So you see this kind of sharp increase in pressure, and then it kind of resolves itself and continues to trend down toward the next diastolic point. Again, we don't need to mark this in any way. We're not necessarily looking at its characteristics, but it is a sign that you're getting good data. So if nothing else, we can look at the waveforms that are coming in, look for that dichotic notch, and if we see it, we know that we are measuring what we think or want to be measuring. And if not, we can then adjust things with how the instrument is attached or recalibrate the instrument or what have you, depending on the system you're using to try to get better data. Okay, so where does this fall in the overall signal pathway? If you've been following along with our webinars this year, we've talked about heart rate variability first and the ECG signal. We then talked about the cardiac impedance measures, DZDT, the first derivative, and now we're talking about blood pressure. And this is sort of the flow with which things are occurring on every cardiac cycle. So you have the ECG signal on top in white. We have a slightly noisy, apologize for that, DC-DT signal in the middle. And then we have the blood pressure waveform with a pretty clear dichotic notch in each cycle in the green on the bottom. And we can just visually see that these things are preceding one another. So the ECG occurs first. That's the electrical activity of the heart. It's triggering that muscle contraction. That muscle contraction is then represented by the DC-DT signal. The opening of the aortic valve is indicated by the B point. The point of maximal blood flow is indicated by the Z, or the point, the maxima of each cycle. And then the closing of that valve as indicated by the X, or the subsequent trough. And blood has to flow out of your heart, right, before it progresses through the circulatory system, before it's reaching those extremities where we're measuring blood pressure. And so then, of course, we're going to see the impact of that blood flow later in the cycle. We're going to see it as it's pushing its way through the arteries and applying that pressure to the arterial walls. So this is the order of operations. This is kind of the full gamut of the cardiac cycle, as represented by these three waveforms. Now, it's maybe slightly counterintuitive because this is not necessarily the order in which you'd want to analyze your data if you are, in fact, collecting all three of these measures for the purposes of something like threat versus challenge assessment or TPR calculation. You typically would you'd analyze ECG, then you'd analyze blood pressure, then you would analyze impedance. So these two are swapped. And we could talk a bit more about that later, and I'm going to, again, talk a bit more about threat versus challenge just a little further along here. All right, so now that we know a little bit about the waveform and what it means and kind of where it sits when it comes to the overall cardiac cycle and the circulatory system in our bodies, I want to talk a bit about getting this data into our application and some of the things we need to think about when it comes to settings. And I'll be able to touch briefly on these again once I open the application, but I wanted to lay these out here first. So we talked about amplitude mattering here, right? We're not just looking at beat to beat timing like we are in ECG. We're actually looking at the amplitude of the signal, 120/80. Are we seeing fluctuations in blood pressure values over time? Which means that the data coming in needs to be scaled properly. It's not always the case that is true. With some of these momentary systems, the data is typically going to be stored in its scaled values. So out of those systems, you're going to get measurements in millimeters of mercury, which is the standard unit of measure for blood pressure. And there's going to be, in a spreadsheet or in a file somewhere, and we can use those just as they are. But when we're bringing in data through our Bionex, like I depicted earlier on a slide, we do need to tell our system what the scaling is from the voltage that's coming out of that system into ours to millimeters of mercury. So we have a couple ways of doing that. I'm not going to get into too much depth because there are some nuanced ways based on the system that you're using. We have a support article on our site that can be very helpful in navigating that. And we're also available to help you if you have questions. But generally speaking, you want to make sure that you are scaling your data to millimeters of mercury correctly, or else your measurements will be inaccurate even if your morphology looks correct. A lot of times with these continuous systems, there will be some sort of calibration mode you can put the system into, and it'll provide some level out of it that is at a known blood pressure value, and then you just look at the voltage and make that a transformation in our software, and then that will just pass through then to your analysis. Okay, blood pressure variability. So, and we'll talk about this a few times over the course of this presentation, but there are really two lenses through which we can look at blood pressure. I'd say most commonly, we're looking at level change. We're just looking at changes in overall blood pressure over time, from baseline to task to recovery. But our application can do some other neat things, things of interest, things that have been and are still being explored in the world of psychophysiology. And one of those is blood pressure variability. Variability, if you've been following along again, is quite similar in one case to heart rate variability. We just want to look at the timing between subsequent pulses. And so to do that, we need to be able to know that we have a continuous series of these points that are being marked on the blood pressure cycles, and there's no gaps in them. And we also need to know what point matters to us. Do we want to look at this from a systole perspective? Do we want to look at it from a diastole perspective? And so we can choose that. We can pick in the application whether we want to use the peaks or troughs as our series of interest for calculating some of these variability metrics. Most commonly, people are using the systolic point for this purpose. I think generally, I'm not aware of a strong case for using the diastolic for variability, but I know for the peak, you'll tend to have more clear morphology at the peak. And typically when we're doing these rate-based measurements, we just want to find a clear and identifiable point that occurs on every cycle that we know with high confidence that we're going to be able to visually or through an algorithm identify and mark. The systolic point is just more defined in general. The diastolic point can sometimes get a bit muddy and harder to differentiate from noise. So we're going to be using systolic primarily for the purposes of this webinar, but you have the option. We like to give you options. And so that's one way in which we're looking at variability. There's another way that we can look at variability, which is amplitude variability. How much is blood pressure varying in an amplitude perspective from beat to beat? And so I'll show you on the analysis screen once we get into the application what that looks like. But suffice it to say, this setting applies to both forms of variability that we might want to explore. And again, I'm not going to go super deep into how we're actually extracting that frequency information, that variability information. If you want a lot of detail on that, I would refer you to some articles on our website or to our HRV webinar that we presented earlier this year. We talk a lot about the FFT, the Fourier fast transform, and how we're actually getting into the frequency domain there. But we are essentially applying the same transformations in blood pressure now, either on the timing between subsequent beats or the amplitude shifts between subsequent beats. Okay, and lastly, baroreflex sensitivity. So we are able to identify in our application when we're using continuous data, these series of points that occur on the blood pressure signal where key changes occur. So in this case, we're defining a baroreflex series of having a minimum length where there's simultaneous change in heart period measured in milliseconds and blood pressure measured in millimeters of mercury. The settings that I have on the screen here and the default settings in our application do match what is typically referred to in the literature, but we like to let people explore, so you can certainly change these as you see fit. And we're going to be able to identify with these two types of baroreflex series, one which is ascending and one which is descending. And I just want to touch on this really briefly because this can be a point of confusion. The difference between heart period and heart rate, they are sort of the inverse of one another. So heart period being measured in milliseconds means that as the heart period increases, which means the time between subsequent beats increases, that's actually a reduction in heart rate. Does that make sense? I know you can't answer me, but I want you to think about that. It's a confusing thing, but that's how we think about it when we think about identifying baroreflex series. Are we having a simultaneous decrease in heart rate and increase in blood pressure, or vice versa? And that's how we're going to tag these as either ascending or descending baroreflex sensitivity series. Okay, so we've talked about these points that we're going to be identifying. We have the systolic and diastolic points on the waveform, and we want to know when those aren't correct. Okay, the data is not always perfect. There's movement that can corrupt data. The algorithms aren't always perfect. There are sometimes signals that are perfectly fine, but let's say the dichotic notch, it's a little too steep for one cycle, and it looks too much like a normal blood pressure waveform such that our algorithms falsely identify it as a blood pressure cycle. We need to know when that's happening so that we can correct it to get the most accurate information out of the applications as possible. This is, again, kind of taken directly from how we handle heart rate variability data. We have a couple of checks that we're performing on the data once it's been identified, once the systolic and diastolic points have been identified. We're going to be looking at whether the heart rate falls within an expected range. And then we're going to be performing the MAD-MED check, which is basically looking at a distribution of beat-to-beat variability throughout the segment and finding outliers that are potentially artifact, not necessarily. You have to always, look and kind of confirm with your own eyes whether that's true or not. In the application, again, if you've used any of our other applications, you'll already recognize this. When something might be wrong, we're going to flag it as yellow, and that will be your cue to zoom in and pay a bit more attention to that particular beat or cycle. These are both settings available in the application. You can turn them off if you want to. Typically, everyone leaves them on because they do a good job. So how are we going to edit? We're actually going to get into the application and edit, but I want to lay some ground rules first and some strategies that are commonly employed. So first thing, assuming that we have done our homework and we know what a good cycle looks like, we need to be able to identify when things were just missed. In this case, this data probably should have been identified, and I may have deleted it just for the purposes of this example, but there are other situations where it's less clear, where the algorithm just missed a peak or missed a trough. It just happens. If you can clearly see the morphology on a cycle-by-cycle basis, and you can just clearly tell that there is a trough missing here, or there is a peak missing here, just insert it. We have tools to do that. And if you're making these sort of corrections to your data, you don't need to count them in any kind of note sheet or something to know how many of these you've made. You don't need to control for how many of them you make. I mean, if you're making too many, you might start to question why it is I'm having to correct so much data by hand, because you really shouldn't. But from a data quality and accuracy perspective, as long as you know you're placing the points where they're supposed to go, you can really make as many of these edits as you want. Sometimes there are just missing points. The same goes for extra points. So I mentioned earlier that there are occasionally situations where the dichotic notch is just such that the algorithm mistakes it for a normal blood pressure or complete blood pressure cycle. And if that happens, or if anything else happens, we'll see a couple examples of other situations where this might occur here in a moment. We can just delete it. We can clearly tell that in this example that I'm sharing here, the 2 points that are enclosed within the red circle are not like any of the others on this graph. They're clearly a part of the dichotic notch. We're just going to delete them. They're going to go away, and everything else is now going to be falling within expected timing, and you won't see any yellow circles anymore. So another type of edit where, delete as many points as you know are wrong, because there's really no harm in doing it. You want to get rid of all those falsely identified points and just end up with the correct points at the peaks and troughs of your signal. All right, there are certainly more complicated situations that can arise, and I'm sure many of you, if you've been collecting data for any amount of time, no matter how much you want your subject to sit still while they're performing a task, or sometimes you don't. Sometimes the task involves movement, although less commonly so with blood pressure. You're going to have periods of time where you can't tell visually, and certainly the algorithm can't tell mathematically where the peaks and troughs should go on the waveform. So in those situations, you have a choice to make. You can, it really depends on the metrics that you're after. So if you're trying to assess variability, then you need a continuous series over time that maintains not only timing throughout these gaps, but also amplitude. I guess that really only matters if you're also looking at amplitude-based variability, but why not do both at the same time? If you can get one, you can get the other, and maybe in the future you would care about it. So in situations like this, if you're analyzing for variability, you'd want to insert midbeats, just like you would in HRV, except this time we're inserting not just one series of data, we're inserting both peaks and troughs, systolic and diastolic points, to preserve both time series. And we'll go over how to do that here in a moment in the application. If you're analyzing for mean arterial pressure or just diastolic and systolic blood pressure, then you can tolerate gaps in your data because we don't really care if it's continuous. We want to preserve, obviously, as much of the data as possible within each segment because we want the best representation of this time as possible. But if there's a gap, who really cares? It's not really affecting any of our resulting statistics. We're just looking at the average systolic level, the average diastolic level, and then the mean arterial pressure that results from that. So in that case, you wouldn't have to perform this estimation. You would just delete the noise and move on. And so when we go into our editing examples, I'm going to edit some segments as if we're editing for variability. I'm going to edit some other segments as if we're editing for just the values themselves, just to really show you the difference. Another point to make here is that sometimes your signal can be disrupted due to the instrument that you're using. So these continuous blood pressure systems use the arm cuff and the measurement at the extremities because the arm cuff provides this baseline level assessment of blood pressure, and then the continual cuffs kind of keep that going for a while. But over time, those do get out of calibration. They get out of range. And so you'll see signal degrade. You'll see values change in ways that are less likely to be physiologically plausible. And so what those instruments will typically do is they will recalibrate at some point. They will take another measurement from the arm to get things back on track so that you know that you're in the range that a person actually is. And so this is great and it's important to do, but you don't want this to happen in the middle of your critical tasks. You want to make sure that you preserve that information. So there are ways in most instruments to set up calibration intervals so that you know that it's not going to occur when it's most important to you to collect this data. You can also disable it altogether. I hesitate to recommend that because you do need to recalibrate them. If you're measuring continuous blood pressure for an hour, you better have a calibration in there somewhere, or else you're going to notice as you're analyzing your data over time, it becomes less and less accurate. But you can time these intelligently. You can plan for downtime in your protocol to allow for this recalibration to occur so that you get the best of both worlds. You get all the critical data when you absolutely need it. And, you get the accuracy that comes along with these calibrations within the protocol. If you need any help with that, reach out to our support team. We can always assist. All right, a few more general recommendations before we hop into the application. In terms of segment length, so this measure is similar to the cardiac impedance measure in that you only need a single cycle to get blood pressure. You can have a single cycle of blood pressure. You can get your systolic, diastolic, and mean arterial pressure values from that one cycle. That being said, we're more often looking at this change over time. And certainly if we're analyzing it for variability, we would need to meet those requirements. They're the same as HRV when it comes to the minimum amount of data you can run frequency analysis on. So we're going to recommend 30 to 60 seconds. And if you are also simultaneously analyzing HRV and impedance, we would recommend that you just match the segmentation style that you've used for those other measures. But certainly if you're, for some reason, looking at blood pressure in isolation, then you have a lot more flexibility with regards to your segment length. In terms of estimation, again, this is coming right from the HRV playbook. We recommend not estimating or mid-beating any more than 10% of your total segments worth of points. We have some tools in the analysis applications that calculate this for you, so you know when you're reaching that limit, but that's still going to be the recommendation that we have. But again, remembering that blood pressure is a bit different in that you don't necessarily have to estimate at all if you're not looking at variability. If you're just looking at level change, you can just delete the cycles that you don't like, the ones that are noisy or are not helpful, retain the ones that you know are good, and then write out your data as usual, while trying, of course, to retain as much data as possible. Which brings me to my last point on data retention. So just like many other situations, we're going to recommend that you keep at least half your segment because you want the cycles that you do have to truly be representative of what was happening physiologically with that person at that given time. So that's our target. Of course, you know, everyone there's not a hard and fast rule here. There's not a published literature requiring that you do this. So each lab may have their own preference, their own set of rules, and that's perfectly fine. You know, you could be as low as 1 cycle and you can still get blood pressure. So it's totally up to you. We're not going to force you to do anything, but this is our recommendation. All right, and lastly, before we get into the application, threat versus challenge. Most of the folks that come to us wanting to measure blood pressure are wanting to assess this nuanced psychological state of feeling threatened versus feeling challenged. And the combination of ECG, cardiac impedance, and continuous blood pressure allows us to do this. We can calculate mean arterial pressure from the blood pressure application. We can then import that information to the impedance application, and along with other information from that application, calculate total peripheral resistance. And we can see here from this chart, which we can send out a reference to this publication afterward if anyone wants to learn more about this. We can see that challenge states are typically represented by an individual exhibiting low total peripheral resistance and simultaneous high cardiac output, and vice versa when it comes to feeling threatened. So pretty cool that we can assess this non-invasively using some of these tools. And I'd say that's a huge point of interest for many folks that we're working with. And editing, fortunately, is much easier when you're just trying to do that. It's harder when you try to do the variability. Okay, so with that being said, I'm going to temporarily take a break from the presentation and hop into our blood pressure variability application to show you these editing techniques in practice. First thing I'm going to do is open a file. And I'm going to start with our baseline data. It's nice and clean. I know that your baseline should be nice and clean. If your baseline's messy, we should talk, or you should reconsider what your baseline consists of. But the way I'm doing this is I'm just going to go to File and go to Open. If you're opening the application for the first time, then you will see a prompt to do this immediately. And the first thing you're going to be asked is to map your channels. I'm going to try not to talk too much in depth about how the applications work because, again, we have lots of resources. And if you've been following along on this webinar series, you've already learned some of this stuff. But we have to tell the application what channel is what. That's relevant if you haven't labeled your channels well, like we have it here. This should be labeled blood pressure, but it's instead just labeled generic transducer channel that it is. This is also relevant if you have dyadic or multiple subjects within a file. You need to tell us which file you want to analyze. So I'm specifying blood pressure. That's really the only signal that I have to map. If we happen to have sources of respiration, that's great because those are relevant if we're looking at the rate-based variability in the application, just like if we're looking at heart rate variability. And so in this case, I am mapping the Z0 and DZDT channels from which I could derive respiration. You could also pull it in straight from a respiratory belt or other system that measures it directly if you have that. I'm not going to talk about segmentation at all because, again, we've gone over this quite often in other presentations. I'd suggest you look at them if you have questions. But in general, we are able to segment our data based on events or based on time, events being points of interest within the data. For the purposes of this webinar, I'm going to be exclusively using time mode. In this particular case, each one of my tasks is separated into a separate file, so I don't really have events of interest in this data. But many folks have a single file with many events of interest within it, and your process would be the same. You just set up the segmentation a bit differently. And of course, we've already talked about this, but just to show you where you'd find it in the application, the tabs to the right of the Events and Modes tab are going to contain your application-specific settings. And you'll probably recognize these values if you were paying attention earlier because I took the screenshot from this file, and it's all the same stuff as you were saying before in terms of artifact settings and all these others. So I'm going to hit Analyze and open up the blood pressure analysis window. I'm going to talk just a bit about what all we're seeing here, and then I want to get into some data editing. So first of all, we have our blood pressure time series at the top. We can see those same points that I was mentioning before, blue points representing systolic points, green points representing the diastolic points, orange X's representing the calculated mean arterial pressure for each one of those cycles. And there's a few more colors that we did not see before. We see these lines, these vertical lines that are going through the points. These are baroreflex series. So these are situations in which the criteria that we specified on the setup screen are being met when it comes to change in heart period and change in blood pressure in subsequent beats. And we can always learn more about them by right-clicking, clicking on the BRS stats, and then we can see the stats that are make up those series. And this is all exported. Everything that you see here is exported in the Excel file when you hit write. So you don't have to worry about jotting anything down. It's all going to be there when you're finished with the analysis. Okay, so if you remember on the setup screen, we specified whether we were going to use a systolic or diastolic point for our series. And based on the selection that we made there, we are going to extract an IBI series. In this case, because I chose the systolic point, the IBI series is indicative of the timing between subsequent systolic points. If I had chose diastolic, it would of course be related to the diastolic points. And just like in HRV, we're going to take that IBI series, we're going to interpolate it, detrend it, and pass it through a Fourier fast transform to obtain the frequency spectrum of that data, with which we can calculate frequency-based statistics. Now, where things start to become different from the HRV application is we're also going to be looking at amplitude variability. So the blood pressure time series, we're actually looking at whichever series we picked, in this case systolic, we're looking at fluctuations in systolic blood pressure over time. And of course, this is a complex waveform, just like the heart period time series is. It's made up of many pure frequencies at varying amplitudes, and we're able to extract those and examine them through the same mechanism, the FFT. So that's why we see the blood pressure power spectrum below it with the frequency of blood pressure amplitude variability represented. And then finally, to kind of round things out, if we have respiration, we're able to do the same thing. We're able to obtain respiration rate and look at correlations between respiration and primary frequencies in the other graphs. Stats are all on the right-hand side. I won't go into each of them in detail. Our manual does quite a good job at doing that. But if you're looking for a value that is derived from this data, you'd be looking over here, and everything's written out to the Excel spreadsheet. So first thing we would do is we would want to assess this data to see if we need to edit it. In this case, we really don't, because I only see one yellow point, and it's right here, and it looks to be reasonably on a diastolic location. The fact that I've chosen the systolic series for all my variability means that I care even less if there's one diastolic that is roughly correct but not perfect. So we can certainly come in here and we can edit this. I'm going to save the editing examples for the next file because they're more interesting, and this one really isn't affecting anything. And we would just scroll through the data. We would look for these situations like this. There's clearly some noise at the diastolic point. So if you wanted to correct it, you could. There is one actually here we should talk about, this spurious beat. So we can see here, obviously the IBI series is quite drastically changing at this one point. And if we look above in the blood pressure waveform, we can see that the algorithm has falsely identified a point of some type right here in the middle of our cycle. And we want to delete that because that is not actually representative of either systolic or diastolic blood pressure. So I'm going to click on the Edit Peaks and Troughs button, expand this window. And now we're in our editor. Again, if you've used our other applications, this is going to look and feel quite similar to what you've already experienced, where we have the ability to insert points, delete points, estimate things, remove things, spline things. The big difference in blood pressure is that we are not only editing one series, but two, the systolic and diastolic points. So we do have to tell the application a little more often, specifically what series we want to manipulate at any given time. And so there are drop downs here for when we want to insert and delete. All the deleting actually works for either point, regardless of what's selected. You do have to tell the application what kind of point you want to insert. And then we also have to tell the application if we're mid-beating, what kind of point we want to mid-beat. So I'm gonna take my mouse, I'm gonna go down here to the graph tools and left click on the zoom tool and pick this one in the top middle, which is my horizontal zoom. That changes my cursor into this little magnifying glass. And what I'm gonna do is I'm gonna click to the left of the noise, and while holding my mouse button down, I'm gonna drag to the right, and then I'm gonna release it. And that is going to zoom me in to the window that I want to see more clearly, to where I want to make my edits. And here, just like we could kind of tell when we were looking at a more zoomed out view, the application simply found a peak where it shouldn't have. Again, these things happen. So in this case, we just want to delete it, and it's totally fine for us to do that. So I'm going to select my delete tool. You can do that either by pressing the delete button, or you can hit the D key on your keyboard. And then you can see my cursor changes into this red dotted circle. And I can expand or contract this circle with my mouse wheel or with this sliding bar up here, this sensitivity bar. And all I want to do is make this the appropriate size so that I can have the point I want to delete within the circle and not other stuff that I don't want to delete. Pretty easy here. And I'm just going to hover over that and click with my left mouse button, and now it's deleted. In the bottom right-hand corner, we have our editing statistics. This is basically giving us a distribution of points and their types throughout the segment. In this case, if I go up to my view menu, I am looking at the peak point distribution. So this is specifically related to the systolic points. And I can see that 100% of them are now falling within the artifact detection algorithms windows. I don't have any that are considered artifact. So I'm probably done here. I'm going to zoom back out so I can make sure that everything looks good. Again, I do see, a couple of diastolic points that maybe are not perfect. We can correct them if we want to. They're really minimally affecting us right now because I've chosen the systolic series as my series of interest. So I'm not going to bother doing that. And I can leave this. And we can see that the IBI series has now been corrected because I have removed that extra beat, and all is well. And we can proceed through the file. And we just keep going like this. The baseline data is pretty clean, so I'm going to hop out of this for now by hitting done. We do want to save our edits. Don't forget to save your edits. It's very unfortunate if you don't. So always save. You can save throughout. You don't have to just save when you're in the application and you're leaving it. You can actually save by hitting Control S on the editor. You can save while you're on this screen. Save often and don't lose your data. All right, so I'm going to swap over to the task 1 file. We'll get into some more interesting edits. I am not going to open up my existing edit file. If I wanted to show you all the edits that need to be performed, I would open this, but instead I'm going to start a new one. Same channels have been mapped. And again, I'm going to be looking at this just in 60-second segments. All right, so right off the bat, we can see that there are some peaks that are flagged yellow in the beginning of our segment. There's quite a few diastolic points that are flagged yellow at the end of our segment, but they're still roughly correct, so I'm less concerned about them. And I'm going to go ahead and hop into my editor to take a look. So again, I'm going to select my horizontal zoom tool from the bottom left, click and drag to hop into this area. And what's likely the case here is this first beat in the segment is just falling slightly out of range for overall variability. It could be related to a trend that was occurring before this segment. The easiest thing to do to get rid of this is to just delete the first beat in the segment. And so if you delete it, you get rid of your artifact, and you're still preserving the vast majority of your segment. You're also still preserving a continuous stream of beat-to-beat timing, which is important for the variability side of things. So perfectly fine when you're editing for variability to remove data at the beginning and the end of your segment, if as long as you're still preserving that minimum 30 seconds worth of data in the middle. You just don't want to do this from the middle of your segment because you'll then inject this gap, and that will cause problems for our frequency analysis. But here it's perfectly fine. So I'm going to zoom back out. And like I said, I could see some situations where the diastolic points are complaining a bit. We could see that the points moving around a little bit, like here it's being flagged a little farther away from the systolic point. Here it's just directly before the systolic point. This is why I generally recommend using the systolic point for the series, because it's just so much more clear, and the diastolic can get kind of muddy as things settle in that waveform. But I would say whether you're analyzing for variability or for just levels, you don't necessarily need to make these edits, because the difference between this point and this point is so negligible over the course of a 60-second segment. Of course, you are welcome to do so if you feel strongly that this point directly before the systolic should actually be the one that's marked. You're welcome to come in here and, using your delete tool, delete the point that you believe to be incorrect. And then using the insert tool, but being careful to select the type of point you want to insert, you can insert a new one. And it seems like overall, the application likes this better, because this is probably more in line with how the point has been specified for other cycles in the file when this kind of noise didn't exist. So perfectly fine to do either of those. Again, when we're talking about amplitude editing, we just want to make sure that we're not skewing our results too much by some wildly different value there. Okay. Segment 2. Now there's some more complicated noise that we need to deal with. Anytime you see this kind of noise, the first thing you're going to do is pop open your editor. So I'm going to open that up. Zoom in again to the area that I think is problematic. And let's see what's going on. So in the beginning of this window, we can see what we would typically describe as a normal blood pressure cycle. We've got diastolic point rising to a sharp systolic peak. We've got a dichotic notch, which is, sort of bordering on what may be misinterpreted as a blood pressure cycle, but we know that's what it is. We also know this because if we look at data that precedes it, these cycles are looking quite similar. So this is what the data is supposed to be looking like at this point, and it's meeting all of our morphology requirements. But then things start to get a little messy. So following this cycle right here, this is potentially reasonably blood pressure, but we can see that we drop all the way down here to something like, 58 millimeters of mercury, which could happen, I suppose, but that change in amplitude coupled with the change in signal morphology would make me think that this is noise. And so I'm going to edit this segment as if I'm editing for variability. So my goal here in editing this segment is to maintain a continuous series of both peaks and troughs. And then the next segment, I'll analyze it a bit differently. So first thing we can do here is we can delete the points that we aren't 100% confident in. So I'd say I'm confident in this cycle right here. From there, I lose my confidence until I get to this cycle, which I think pretty clearly looks like the cycle next to it and the cycle next to it. So this period of time between these two known good cycles, I need to insert some sort of estimate that preserves timing and amplitude, or at least skews those metrics as little as possible, which is what we're able to achieve with the mid-beat. So there's two ways that we can delete these things. I'm going to show you a new one because I've already shown you how to delete the individual points, and that is using these X cursors to delete groups of points instead of just a single point at a time. So what I'm going to do is I'm going to hover over this blue cursor with my mouse, left click, and drag it until I'm beyond the systolic point of the last cycle that I think is probably not actually blood pressure. It's some kind of noise. I'm going to do the same thing with the other X cursor, but this time I'm going to bound the noisy data on the lower end. So now I have these two cursors that are sort of outlining the data that I think is problematic, that may not actually represent true blood pressure cycles. And I can use this button right here to delete all the points between my X cursors. So with one button press, I've now gotten rid of all of this noisy data, all these points that were marked that were not necessarily actually points of interest. Okay, now I want to do this estimate. So I'm going to use these cursors again, and I'm going to drag the cursor so that it's before the diastolic point of the last known good cycle and after the systolic point of the last known good cycle. So remember, the diastolic point can be thought of as the beginning of a blood pressure cycle. The systolic is not the end, but it's sort of the end of the area of interest for us when it comes to the blood pressure cycle. And so we want to estimate those points between these two areas. So now that I've done this, I can see that my midbeat tool has lit up, and the application is suggesting that I need to insert 4 midbeats between these points. So I click that button, and it's going to insert them. So we can see right away that the timing is now passing the artifact detection algorithm's requirements, given that all of these are blue, none of them are yellow. The estimated points are going to have these orange crosshairs around them, just like you'd see in our other applications when you're estimating things. And we've also maintained amplitude as best as we can. What we do is we take the average amplitude between your start point and your end point, and we just place them all at that exact amplitude. So it's not perfect. No estimation ever is. But our goal here is to maintain the continuity while minimizing the skew that it provides to your data. So just like we did with systolic points, we need to do the same thing for the diastolic points. So, and just like with inserting points, we need to tell the application what kind of point it is we want to work with. So I'm going to change this from peaks to troughs. Again, now the application thinks we should have 4 here. That makes a lot of sense because if you have 4 systolic, you should have 4 diastolic to match. And I'm going to hit that button, and now we're going to have our 4 diastolic points inserted. Timing is less critical here. We're not using that for timing anyway, but it does preserve an average timing throughout this window. And so now we have, in a previously very noisy segment, estimated systolic and diastolic values if the noise had not occurred, maintaining both amplitude and timing to the best of our ability. And from there, we would just continue to work our way through the segment, just like always. We can see down here in the bottom that we're not done yet. We still have 4 beats that are being marked as potentially artifact that we do need to correct. So I'm just going to scroll through here. I'm using, there's a few ways to scroll through the data. You can drag this bar around up here. You can select the hand tool and drag the data around. But the way I like to do it is by using the left and right arrows, which increments through your data in 1-second chunks. I think it's just a really nice way to traverse the data, to see it with sufficient clarity, and you're just moving at the right pace. And so I'm just going to keep scrolling through here, hitting the right button over and over again until I see something else that requires my attention. Here I can see that, like an earlier example, the application has falsely added a point here, so I'm just going to delete it. Now everything's happy. Here, the application has missed an entire cycle. So we can see here that the cycles are starting to change a little bit here. It's possibly due to, finger placement within the finger cuffs, or a number of things could potentially cause this, but these are still valid blood pressure cycles. They're just looking a little different. And so what I would do here is just insert the points that the application missed. So I'm going to switch over to my insert tool. I have already selected troughs, so I'm just going to start with the diastolic point. And remember, the diastolic point is the low point preceding the sharp rise to the peak. So I'm just going to click in this area. It's going to find the trough in that area. And we can see once I've added that point that the surrounding data is now falling within the bounds of the artifact detection algorithms. So we know we're doing the right thing. Of course, we need to match that with a systolic point being inserted. So I'm going to switch to peaks. I'm going to do the same thing here, click. Now we've restored timing, we've restored amplitude, we've added a cycle back into our data. So this is great. Okay, I'm going to keep scrolling here, and I can see that there's obviously a cycle that does not look like the others. Something happened here, probably movement to disrupt our ability to measure blood pressure in this case. You can't necessarily fully trust the diastolic markers on either side of this. You could if you're not particularly interested in the diastolic series, but in my case, I'm just going to delete both of these and delete the peak because I can't say for sure that any of those are correct. I'm going to, again, move my X cursors so that I'm bounding the low, the earliest diastolic marker and the latest systolic marker or diastolic marker. And I'm going to insert a midbeat with the troughs specified to insert 2 diastolic points. which is what we figured would be the case. And then I'm going to also insert one peak, which may have occurred somewhere roughly around in this area if the noise hadn't happened. And so now with that edit, we can see that we've cleared all of the artifact points from our segment. We've also only edited 6.2% of our data in the form of an estimation, meaning that we've stayed within our 10% bounds. We are happy. This is all within our recommendations, and so we are done. We could just do a quick scan through the rest of the file, but then this is the end of it. And so we would just exit back out, and we can write our data and store it from this point. All right, I want to go over one more example here before we get into Q&A, because hopefully there's lots of questions. But I wanted to edit this segment through the other lens. So we've talked about, in segment 2, this is the way you would edit your blood pressure data if you care about the variability statistics. But if you're assessing something like threat versus challenge, you might only care about systolic, diastolic, and mean arterial pressure, in which case we don't need continuous data. We just need to get rid of any cycles that are not truly representative of a person's blood pressure within a given period of time. It actually makes our life a little easier. So I'm going to edit this segment as if that was what I was going for, if that was my goal. So I'm going to edit peaks and troughs, expand my editor, and again, zoom into the first area of noise so that I can decide what to do. So we can see here that we have pretty normal cycles of blood pressure leading up. And then we have this noisy section where, there might be some in here that look somewhat like what we'd expect blood pressure to be, but they're surrounded by noise and their average amplitude is quite different than what we were seeing before that noise occurred. So better safe than sorry. You're not trying to preserve all your data here, just as much of it as possible. I'm going to opt in this case to simply delete the points that I'm not supremely confident are accurate representations of blood pressure. So I'm going to come out here. I'm going to move my X cursor to the right, to the left, I should say, of the cycle that I can see that's quality out here. And then I'm going to move my other X cursor so that it's just after the last good cycle that I see over here. And I'm going to delete them all. You'll see that the points on either side of this gap are going to be marked as yellow. This is because there is a gap here, and we don't really know necessarily if you're editing this data for the variability stats or for just amplitude level stats. So we want to bring attention to the fact that this is representing a gap in data. That being said, you knowingly did this. I knowingly did this because I don't care if there's a gap. I just care about the levels. And so in this case, even if there's yellow markers here, we can safely move on knowing that we created these conditions intentionally. So I'm going to scroll through this segment a bit more and continue to identify situations. So again, though, even if you're editing for amplitude based statistics only, we still don't want these false positives. We don't want these points that really shouldn't be marked as anything to influence either of our calculations. So in this case, just like before, I'm going to select my delete tool. In this case, I pressed the D key on the keyboard to select it as a hotkey, and I clicked there to delete it. And you would just continue to move through your data like so, looking for things that need to change. So here's another example of a point that was erroneously added. I can just delete it. Here we have a case of looks like a complex that was missed. So this isn't perfect. I mean, I think it wouldn't be wrong if you were to say, I'm just going to leave this out because I don't know for sure if it's blood pressure, but looking at enough data, I mean, you can kind of see you've got your diastolic point here, your systolic point here, and then your slightly abnormal, but still in the right location, dichotic notch following it. So in this case, if we want to be as correct as possible, we can insert this. So I hit I on my keyboard to activate my insert tool, and I'm going to click so that the peak is within the dotted circle. I'm then going to switch to troughs. I'm going to click so that my trough is within the dotted circle, and we can see that timing is all aligned and the beat looks good, and we can keep going. Here on this cycle, Again, if we just were to compare the morphology of this to the other beats that surround it, we can kind of tell that this point that's selected right here is the actual systolic point, and that whatever happened here is related to motion artifact. It's not actually your systolic point for that cycle. So by simply deleting this point, we can preserve the systolic and diastolic blood pressures for this cycle. And then the fact that the noise happens afterward is of no concern to us because it doesn't impact any of our stats. We're just ignoring it. And as we continue to move through, you know, there are some points here we should probably just delete because we can't really tell what's going on here. The morphology gets a little odd throughout this section. So you could take a sort of aggressive approach and just delete all the points between the noise. So it looks like we have to come all the way out here before we start to see clean data again. So you might delete everything from here to here. Although there are some good cycles in here that you could probably preserve if you wanted to work on it. For example, you could insert a trough here and a peak here because this is still pretty clearly following the expected morphology of diastolic, systolic, and dichotic notch. It's sort of up to you, the extent to which you want to analyze this, obviously balancing the effort level with the value that it provides. Okay, so I want to make sure we have plenty of time for Q&A, so I'm going to hop back over to my presentation. And again, I'm not going to save these for now, but always save your edits. You don't want to do this twice. It's no fun to edit more than once. So let me pull back up my presentation. 1 second. Switch my screens. Okay. So before we get to Q&A, I just want to bring awareness to a few resources that exist on our website that I would encourage you all to use to the best of your ability, because we have it out there and it can be very helpful. Support.mindwaretech.com. You can go there to download the latest versions of our software. You can create support cases, which will end up in our queue so we can help you directly on maybe a more complicated problem. We have options for self-paced training as well as one-on-one training with our staff. And we list out events here. So we run webinars like this. We're always, looking for feedback from folks in terms of what they want us to cover. So give us your feedback. You might end up being able to attend an event that was inspired by something that you asked for. And then we also run annual seminars in person. We just did one in our hometown of Columbus, Ohio this past August. We're going to be running another one in Denver, Colorado, if all goes according to plan, in the summer of 2026. The registration should be up for that soon. And that's a really wonderful opportunity to learn from experts in the field, to meet other like-minded individuals who are studying these parameters, and it's just a really great time. So definitely encourage you to pay attention to the events that we have coming up so that we could see you at one of them. We have a newsletter that we do send out. We very sparingly on our newsletter. I hate receiving newsletters or ads every day from companies. I delete those promptly. I don't want to be that. I don't want us to be that company to you. So sign up. You won't hear from us that often, but hopefully when you do hear from us, it will be genuinely appreciated content. So generally quarterly is what you're going to see those. And you can sign up for this newsletter on our support site as well. And then, like I mentioned, if you need a bit more help, we do have the option of either paid or complimentary training sessions, depending on where you are in your journey. And so if you want that more personalized, hands-on touch with us, just reach out to us and we're happy to help and schedule that sort of thing. And lastly, before we get to Q&A, we do have training guides, and a lot of what I talked about, a lot of the things we've talked about in past webinars, they're detailed quite thoroughly in these articles, and you can learn about the algorithms, where they come from. We don't develop our own algorithms here. They're all from peer-reviewed published research. I would encourage you to go there, learn as much as you can, understand how these things are working. It will only benefit you as you continue to incorporate this into your research. So at long last, your questions. I'm going to take a moment and look at the questions that have come in so far, and I'll just start answering them. So if questions, if you haven't submitted your questions, again, you can do so through the Zoom interface. Please start sending them in, here for the next 15 minutes to address anything that might need to be addressed. Okay, so first question I see here is a question about workflow. So what order should these measures be analyzed in if we're looking at HRV impedance and blood pressure? So I mentioned this briefly earlier, but the correct order for analyzing these would be to start with HRV, then analyze blood pressure, and then analyze impedance. And this is also assuming that your ultimate goal is to calculate TPR for the purposes of potentially threat versus challenge assessment. And so by starting with HRV, you're going to clean up that ECG series, which you're going to need ultimately for the impedance application anyway. Then you're going to move into blood pressure. You're going to clean up that series so you can get clear systolic and diastolic values. You're going to save those data out to the Excel spreadsheet. And then in the impedance application, we have an option to import your blood pressure results so that we can use the mean arterial pressure values to calculate TPR. And so if you do things in that order, that is the optimal workflow to getting there. Okay, so I have another question about non-continuous blood pressure. How often should I be making measurements to accurately capture mean arterial pressure? And so earlier, I think I might have glossed over this, but earlier on in the presentation, I did leave a little tip to take a look at a publication from the late 80s that refers to the frequency of blood pressure measurements and the ideal frequency for those. So that's typically what we refer to when we make suggestions like this. I think other folks that are doing this in practice, I've heard, are taking measurements every minute for super critical tasks. That can be pretty uncomfortable for the subject. And so you want to balance subject comfort with the granularity of measurement that you need for whatever it is that you're studying. So every minute I've seen certainly every other minute or every few minutes with a break in between, because that can, again, just become quite tiresome for the subject to have this thing continually squeezing their arm. So really, I guess the moral of the story is as frequently as your population base will tolerate. But once every couple minutes is probably good enough. All right, let's see what else we have here. Okay, can I report on challenge and threat without measuring blood pressure? So if you're planning on using physiological markers to assess threat versus challenge, the answer is no. There are not other known markers that correlate with those two psychological states without calculating TPR. There are some interesting things that are being explored with measures like pulse wave velocity that have promise. And then there are new technologies coming out, such as cuffless blood pressure, that are starting to actually receive FDA clearance for measuring blood pressure. Some exciting stuff there. Not research grade devices. These are typically medical grade. They're not going to integrate well. There's some challenges to using them, but they at least reduce some of the subject comfort burden that these other devices have associated with them. So hopefully at some point in the near future, sure, we'll have to measure blood pressure, but maybe we can measure it in a way that everyone is a bit more comfortable with. But for the time being, if you do want to assess that particular thing, you need to collect these measures. All right, another question on momentary blood pressure. So with a CareScape in particular, how can the instrument be controlled in Biolab? So it's a fairly new integration. I mentioned it briefly on an earlier slide. Let me just get back there real quick. Here we go. So this blood pressure screen and this integration is actually only available in the latest version of Biolab. Fortunately, Biolab is totally free. So if you want to download it and use it, as long as you have other MindWare hardware, you can just use it to collect blood pressure data in Biolab. And so there's a special cable that we've designed that connects between the CareScape device and the PC that is running BioLab. And with that, we're able to press buttons on this screen-based CareScape device, and they kind of mimic the buttons that exist on the actual device. So if you press the green button, you can inflate the cuff and take a measurement. Those measurements are then stored as event markers in the file with all of the values of interest, systolic, diastolic, and mean arterial pressure. And then you can extract those later and do whatever you want with them, including doing something like a threat versus challenge assessment if you wanted to do that. The other cool thing about software controlled setup, as opposed to just pressing the buttons on the instrument, is we can schedule things and we can cycle things in more complex ways. So within BioLab, we're able to tell the device, I want to take a measurement every so many minutes. And I want this to repeat 10 times. And so you can, per the needs of your protocol, adjust that and then ensure that this is automatically happening. You don't have to press a button, you don't have to think about it. It just takes the measurements, stores it back in BioLab, and you're good to go from that point forward. So if you have questions about that, if you have a CareScape sitting around and you don't have one of these cables, reach out to us, sales@mindwaretech.com or info@mindwaretech.com, and we can have that conversation, talk to you about what it would take to get your CareScape more integrated with your overall system. Okay, another question about calibration. So I'm going to hop to, let's see, this screen. So the question is, my CNAP calibrates every 15 minutes and interrupts my study. Any advice? Yeah, my advice is to change the setting on your CNAP to not have it calibrate so frequently. We don't have any examples of that on my presentation, but sort of in the same menu system as what's depicted in this picture here, you can go to a setup screen where you get to define the interval at which the system calibrates. And you can push that timeout as far as you need to allow for all your critical tasks to take place. And you could actually I think you can even disable it, although again, I wouldn't recommend it because you do need to calibrate. You just need to intentionally schedule those calibrations based on the needs of your protocol. Okay, those are all the questions that have come in. So, we have another 10 minutes here allocated to this presentation, so I'm happy to hang around and continue to ask questions if anything comes up at all, or if anything were to come up after this presentation ends. If you get back to your lab, you start collecting data, you start having questions, we're always available. support@mindwaretech.com is the email address. Send us an email. We will gladly help you out with the questions or issues that you're running into. And then I believe you should be asked to take an exit survey when this is all said and done. So we do really value the feedback that you provide us on those surveys. They help us to plan for future webinar offerings. And so, like I said earlier, please tell us what you want to see, what you want to learn more about, and maybe the next webinar will be directly driven by your feedback there. But if there aren't any questions and you have to run, thank you so much for your attention today. Thank you for joining us. And we look forward to seeing you at a future webinar.